Okay.
Okay.
Great. So any questions from the audience? You can type in the chat if you don't want to speak up or not able to speak up. Yeah, so if no question from others, I do have a question. So I feel like the pipeline the pipeline you introduced, is that some industry grade pipeline, or is more of a you build the pipeline based on open source frameworks?
So yeah, so it was a open source code from AWS. That's the RAG pipeline deployed on AWS. They were using some open source models like Llama, and then we used the pipeline, and then we deployed the pipeline on whatever they use, the instances, and the instances that they specified. And all the experiments, I think I didn't say that explicitly, but all the experiments are done on AWS here.
Hmm.
So model the using certain trace patterns, right? So we model the network latencies, we model the overheads of virtualize and everything that because we run it on AWS.
I see. Then regarding the, let's say, the how do you evaluate the also so the design itself, I mean your contribution is more focused on the in-story acceleration. You didn't change the other part, right?
We didn't change the other part, yeah.
I see. Yeah, then another question is, so this racket-based pipeline, how is it too different from the existing like agentic AI system? How different they are?
So that's a good question, and this work we did when agentic was starting. But actually, if you see agentic, so RAGs are significantly used in agentic pipelines today. We have a lot, right? So in fact, this idea would apply to agentic as well. And I didn't add it to the slides, but I just simply Googled a agentic pipeline that uses RAG on AWS, and they have very good. And also, I guess Anthropic has some figures. I showed a very simple pipeline which has a data retrieval, right? But they have extremely complex branching to some database, and then there are like different branches. Some branches get terminated based on certain conditions. So basically, what happens, the LLM is again defocused even significantly, right? Here, LLM was one of the three, but now if I have 10 and only one of them is LLM, so then you really need to understand how the data flows between this complex, data flow graph. In fact, it's a data flow graph now. So, and then if the LLM is not significantly contributing as per Amdahl's law, then what are the other parts? Or how can I really make the LLM the significant part? That is what, because we have been spending so much, investment into accelerating LLMs and makes sense as well. So I think that's the meta point here. But I think that's a good question that you asked. I think agents will significantly benefit from these ideas.
Yeah, I agree. I saw some papers, I think from this year's HPCA, is demystifying the cost of the
Minsu, yeah,
yeah,
Kayast.
yeah. So
Yeah.
that paper was talking about how to, I mean, they basically characterize the cost of Gen AI, right? Then the cost is the kind of a crazy. More kind of half of the system is idle because of all this kind of pipeline in the system. So
Pipeline.
there's a huge room to improve the entire system.
Entire and the other thing I really encourage everyone, right? In isolation, problems change. Like, yeah, in isolation, if I'm accelerating LLMs, yes, LLM is the bottleneck. But when I move the problem to a different, like let's say to a pipeline, then the bottlenecks that appear, they are really different. So and then that today has a huge opportunity because these new agentic pipelines, where are the different bottlenecks that are emerging because we have this complex pipelines. I think it's a very good and interesting area
Yeah,
to look.
I agree. Okay, cool. So yeah, we probably can continue.
Okay, let's
Thank
go
you.
to DMX, right? So the first RAGX, what I tried showing is we have a GPU. We want to supply some data from a database, and then we need to, supply it fast, quickly, so that my GPU is not, underutilized or, waiting on my data. And let's just call it the metadata processing. We need to accelerate the metadata processing before, running it on GPU. However, the next PMX, right? Here, what happens, there are certain intermediate data that also I need to transform or process. And there are certain use cases for this. Let me take an example and then show. Okay, how do I, next, okay. Yeah, let's take this video surveillance application, which is basically something like, there is a video decoding that is happening, uh, which basically is converting raw footage into usable frames. And then you have a object detection. YOLO neural network was very famous for object detection, which identifies and locates, people, vehicles, or other targets. And then you have a data analytics stage, which then, let's say, counts how many objects were present in the frame and localizes sometimes. Now, each of this stage produces intermediate outputs, right? These intermediate outputs needs to be consumed by the next or the stage. For instance, video decoding produces something that object detection consumes, right? And I guess this slide is much better at that. You have an initial tensor, and then you produce some intermediate output that object detection consumes. However, individually, these let's say kernels are, we can optimize them. However, each of these kernel requires data in a specific format. For instance, the object detection YOLO requires maybe brain floating point BF16 inputs, and then in a certain tensor, 4D tensor or something, and then it outputs again brain floating point. However, the data analytics requires at a different, format. So just passing data is not necessarily true today. We often have to reconstruct, reformat the data, the intermediate data in between many times, right? So I spoke about domain-specific accelerators like GPUs and TPUs and many other accelerators, right? And they can provide significant speed up. And it makes sense that we offload certain kernels that are acceleratable to these accelerators. Right. So what happens, let's say we use accelerators like a video codec accelerator. Google has a video decoder accelerator. There is a TPU that can accelerate the object detection. There are a lot of accelerators for data analytics, right? And then if we look at the system that, operates these accelerators, accelerators are generally attached to a CPU over an interconnect. You have some interconnect. So you have the data, you move the data to the first accelerator, you accelerate it, you speed it up, right? You have to move the data back to the CPU. You need to restructure the data, let's say convert it from, some data type to another data type or some shape to another shape, and then send it back to another accelerator, and then do the process for this chain. And these accelerators need not necessarily be by the same vendor, and vendors have certain specifications of what data type they can input and what data type they can output. So this constant back and forth over the interconnect plus this repeated CPU side formatting that we are doing for the data becomes a major source of inefficiency in this multi-accelerator pipeline, because I have multiple accelerators. We have this now new inefficiency that is at the intermediate data level. I think which I've highlighted in green here, and then let's term it as, data motion. If I have to define data motion, it's this data movement of sending data over PCI to the accelerator. Multiple times I'm sending. And then there is also this data restructuring part that I need to restructure the data, change the type, maybe quantize it, dequantize it, something like that. Right. And then we take this idea and then we profile it using some systems and some benchmarks, and we see that the runtime of domain-specific kernels, right? Let's say we have a CPU. Let's say we have everything running on CPU. There's no accelerators here. Obviously, what happens, the kernels, right? The object detection kernel like YOLO, they dominate. But let's say we now accelerate these using some accelerators like TPU. So now naturally the kernel will reduce because I'm able to accelerate. I have three different state-of-the-art accelerators. So I am able to reduce maybe 80% of the runtime. But now what inflates is this other part, right? Data restructuring and data movement, because now I have to move the data, I have to do some processing on the CPU. And this limits the overall speed up. And how do we unlock the performance or potential of these accelerators? We are using expensive accelerators, right? So let's revisit back. to this figure, and then how about we can just remove the restructuring? Let's say using some magic, I'm able to remove this data restructuring from the CPU. I can get some, latency back. How about using some other way I can remove, some of these data movement, right, to the CPU? Then this is an ideal system where now I don't have those overheads. And this is exactly what we do with data motion acceleration DMX, where what we do is we have some unit here. I'll go into the details of this unit, but we have some unit that is able to, we have some specialized unit that is able to what it is able to take on this role what CPU was doing, what like for instance data type casting, reshaping, flattening, encoding, quantizing. It'll do everything. It'll connect to accelerators. It acts like a glue between two different accelerators and transfers the data without going to the CPU. And that's the entire idea for the, data motion acceleration, with that to eliminate this interconnect round trip and the restructuring overhead. But how do you do it even? What is this compute unit that performs the restructuring? What is the compute unit? Where is this even placed in the system? I just showed a figure where, okay, we have removed certain things and then placed it somewhere, right? We need to really make it concrete what exactly it is doing and how we are doing. So to do that, we take different data restructuring kernels, and then we profile these kernels on Intel, on CPU using Intel vTune. Intel vTune is used to profile is a very good, tool to find the bottlenecks on the CPU. And then this figure breaks down the bottlenecks. What we find here is that the data restructuring kernels are predominantly backend bound in a CPU. When I say backend bound, it means that we have a very high data cache miss rate because it's largely streaming pattern, right? These are data parallel kernels. So I'm thrashing my cache, CPU cache. And then there is very low, functional unit availability. What I mean is, CPUs have limited resources, limited thread counts. Uh, at the same time, you see the front end stalls are very low and there is very less branch misprediction because these again kernels have very simple control logic and they're data parallel. So this suggests that the workload is kind of memory bound and compute regular. So which is actually a great fit, right, for accelerating. It's data parallel, it's memory bound. I can now design some accelerator. With that in mind, what we did is we designed a DRX accelerator we call data restructuring accelerator. I'll not go into the details. It has four different parts here. The first is a programmable front end where you can program it using, instructions. There is a restructuring engine. We have restructuring engines. We have transpose engines that are used, and then we have programmable off chip, which are controlled by the compiler. If someone is interested, I'll recommend them reading the paper, and then there are one or two other papers which kind of motivate this accelerator. But however, or we can discuss offline the details of this architecture. But now that we found out the what this compute unit should be, and just to summarize, the way we find out is we profile it using vTune. That's like, and then you find out what are the bottlenecks. Based on the bottlenecks, next you come up with an architecture. Once you find out where do you even place it, right? Where in the interconnect do you place it? Again, in the paper, we explore multiple placement options. For instance, the DRX can be placed right next to the CPU. However, if I place it there, it is still limited by this interconnect, right? That connects the physical pins that connect to the CPU. I can't increase my bandwidth, right? It can be, placed within the interconnect. Then what happens, I still have to go through, one round trip to get to a DRX. And then how many DRX should I even present? It can be placed next to each accelerator, which requires that when I manufacture an accelerator, the manufacturer has to embed DRX, which has some cost. It's not free of cost, right? Or it can be placed on the, network switches, because when I'm manufacturing a switch, you can go and integrate. We have multiple different, placement configurations that we explore the pros and cons. Every configuration has a pro and a con. And it's not necessarily that we are advocating one type over the other, but based on use case, someone can choose certain design. What I showed here is we used a small PCI switch to attach a DRX. So you can still manufacture the accelerator as it is. You have a PCI switch, you can add a PCI switch, and then you can add a small DRX here, which we call bump in the wire. Right. And then what we do is we evaluated this DMX using 5 different benchmarks. We have different kernels, like for instance, you can see on the first column, and then the second object detection and some other. And from different, workloads. Some are database, some are video surveillance, some are brain stimulation. Uh, and then there are these data restructuring operations, for instance, some are concatenation, flattening, and max pooling, right? And then we have different systems that we compare against. I think here we mentioned 2 systems. Everything is realized on, we do all the experiments on AWS EC2 F1 FPGAs. We are designing accelerators, but FPGAs are a great resource to, kind of like prototype and see what the benefits are in a real system. One is the multi-accelerator system where we run everything on CPUs, and then the other one is DMX, where what we have is this tiny accelerators where we offload the data restructuring. I'll quickly show the benefits. So this figure shows the performance improvement of DMX over multi-accelerator system. The y-axis again shows the different benchmarks. For each benchmark, here on the y-axis, we show the speed up relative to the baseline, which is when everything is being done on a CPU, right? DMX on average achieves 3.3x speed up. And this speed up is over a system that already uses accelerators, and then the data restructuring is done on a CPU, right? And I think, let's see if I have another figure. Yeah, I have another. And then this figure shows the runtime breakdown. I think this is a much more beneficial figure here that shows, in the baseline system, what happens. Most of the part is on data restructuring because you have accelerated the kernels using 2 or 3 different types of accelerators. But now using DMX, you again accelerate this data restructuring part. And now what happens? The kernels are the bottleneck. So now you can go and improve the performance of the kernel by using software techniques or systems techniques or, accelerators or better accelerators. And across all of these, papers, like I didn't list other papers. We have some other papers as well. We use neural models directly from, Hugging Face. We prototyped on FPGAs. We synthesize everything to get the area and power. I also didn't present the area, power numbers, and the cost. We have those in the paper. But the way we could do it is using GeneSys, which is an open source parameterizable NPU generator with full stack compiler. It has a compiler as well. It can lower code from Python directly to our accelerator. It has an accelerator, it has systolic array. It has another processor, which is a vector processor. We call it tandem processor. It's an ASPLOS 2024 paper if in itself, if somebody is interested in the details. But this models an entire architecture that can run, for instance, BERT end to end. You can offload BERT directly to this accelerator and it can run. It has it's entirely written in Verilog, and then it has a compiler that can take a PyTorch Onyx model and then directly, uh, generate the binaries. Uh, we have verification infrastructure so that you can do RTL. You can change the code and then you can verify as well. We have APIs, for instance. This is the API to run ResNet, right? Just 6 different commands. You load the driver, you initialize run, and then I guess the last 2 are not even necessary to run. So just 4 different APIs. If somebody wants to really leverage, accelerators and run their, ML models. And the other reason why people want to run ML models is, let's say you want to study some software techniques such as quantization, right? And then you want to study on accelerators. So what you can do is you can take GeneSys, you can run it, deploy it on AWS, then you can take the model ResNet, run it, then you can quantize ResNet, again run it, and then see is it improving performance or not. And then finally, it runs on AWS, so you can take some EC2 instances and then take the GeneSys driver and then the code and then run it on AWS. I think we also taped out, and then on the FPGAs we had GeneSys running. So these are some pictures that I had. And then yeah, we also created YouTube videos. So if anyone wants to just follow the YouTube videos and run, I guess that's another option. And you can use the barcode to get access. So the conclusion here is, right, when it comes to deploying AI applications in data center, the data exchange between stages sometimes curtails the assumed benefit, because we are accelerating neural networks, we are accelerating databases, but then sometimes the data movement is what curtails these benefits. So taking this holistic systems approach where rather than just designing an accelerator, thinking about how this accelerator is used in a data center context in the end-to-end application, and then how the data is supplied to the accelerator. Is there any other problem that curtails maybe my accelerator from getting the data in the right time? That can unlock a lot of opportunities, and that opens up a lot of research questions in systems architecture, co-design. Uh, with that, I think I'll just quickly talk about the current work that I'm doing. I work at Microsoft. This talk was my PhD work. This was until last year, but I want to quickly present about our group at Microsoft. It's called Azure Research Systems. The main aim of our group is to improve the efficiency of data centers. And when I say, it's a very broad spectrum of work that we do. There is efficient AI, where we are trying to improve the performance of inference systems in the data center, how data centers are even designed, how do you co-design the cooling aspect, the power delivery aspect in the data center. That is another aspect people are working on. And there is entirely another serverless aspect, where how serverless deployments work in data center, and what are the different systems, how you can improve the efficiency of serverless systems. That is another. Then there is a lot of work on sustainability and sustainable SKU designs. How do you design servers that are sustainable, that have a minimum carbon footprint. Uh, and then I think there's a lot of work on applying ML for systems. The first one, efficient AI, has two parts. One is systems for ML, and the other one is ML for systems. And then we have openings constantly. I mean, where we put up openings if we have openings, but yeah, if someone is interested, it's encouraged, you can apply. But with that, thank you very much. And if there are any questions, you can ask right now, or please feel free to email me. Uh, I can put my email in the chat. I see that I didn't put the email here. Dot. I think it's a very easy email. My email.
Yeah.
Okay, question as well. Let me see.
Yeah, thank you. Yeah, and we have a question from the audience. So the question is, when you showed the DMX speed up, how large was the batch size? Do you think the data movement would be more of a bottleneck for low latency and a small batch size?
That's actually a good question. And in the paper, we have sensitivity varying the different batch sizes, varying the number of, stages that the data moves around. And in fact, all of these experiments, I think that I presented was based on latency, for low latency. But we also have another experiment that shows throughput. Throughput and latencies are not necessarily reciprocal of each other, and that's why we have another experiment that shows throughput. At a very high throughput, what happens, where we don't really care about latency, but we want to make sure that our system has a certain throughput. But the result I showed is for actually a low latency and batch size of 1. And I think the other question is, what's the favorite part of what you do? I think that's a very deep question. I think what's the favorite part of what I do is, first of all, I think just identifying, I think, problems that lie at the intersection of, when I look at end-to-end applications, there are there's certain small aspects where there's some problem. And once you identify, that is a very, very kind of like, surreal moment where you are like, okay, I found a small problem that lied in some intersection, and I think that is my favorite part, I would want to say. But also the other favorite part is, talking to so many people and then learning from them and interacting with others, and presenting the ideas that we came up with. I think while especially talking, you get a lot of feedback and questions that really make you think again. Oh, I actually missed certain part, maybe I didn't miss certain part. That is another favorite thing. But yeah, thank you very much for your time. I think it's very late there in Florida. I guess everyone is in Florida.
Yeah,
And
not necessarily. The
oh,
first question from Marco, he's in the AMD research now. He's a PhD student with me. So he's actually in Bay Area. If you like, you can, find some time chatting with him.
oh wow, that would be very nice. Yeah, yeah,
Oh,
yeah.
by the way, he is a Badger. He did some research with Matt during his undergrad in Madison.
Oh, okay. Yeah, please email me and yeah, we can meet. Always looking to meet new people. I mean, I moved from San Diego and then I don't think uh, yeah, let's meet sometime. And then thank you for inviting. I think it was a very good opportunity.
Yeah,
Uh,
thank you for the great
So I
talk.
think I have one more question. I don't know if my understanding on your presentation is correct or not, but
uh-huh.
for your DMX design,
Yes.
is that something like domain specific, like it is specific for like two different accelerators? I mean, like it is case by case stuff.
So yeah, let me clarify. I
Yeah.
think it is not specific to any accelerator, even agnostic to different manufacturers. Like you can
Okay.
use a Google TPU and then maybe a GPU. It's a programmable accelerator. There are certain compiler instructions, and then you have certain operators that you support. If the data restructuring goes beyond the kind of support, I mean, the instructions that we support, then yes, you can't use DMX, but otherwise it's a programmable accelerator. So I hope
Okay,
that, yeah.
so it is like generalized to many accelerators. So because the data reconstruct reconstruct is actually very like I think not many person not many people think about. Yeah, I think it's a very interesting topic because I also meet these kind of issues on like replay the other person's accelerators. Like I need to reconstruct their data. Yeah, thank you very much.
Right? And then just to add, let's even not think about accelerators. The way you write programs is by using functions. You have different functions, right? And then let's say somebody has written a function like in a C++, right? The header file. You define the API or the function signature, right? What is the input that you expect? What is the output that you expect? And let's say the header file for especially libraries, it's already defined. I use it, and then if I want to use 10 different functions, I call one function, the output comes. I generally need to maybe tile the output, maybe restructure the output so that my next function can consume it, right? And that has been true generally in programming as well. And when we move to, deploying it in accelerated systems, each of these functions can be kernels, right? And then when we use accelerators, this problem actually inflates, which I was just trying to show. But it's good to know that you also faced similar issues.
Yes, thank you.
Thank you, thank you, thank you very much.
Yeah, so I think we have a good amount of discussions. I'm not asking you more questions. I will catch up with you later. So thank you again for giving us this wonderful talk. So yeah,
Thank
I will see
you.
you later. Thanks
Yeah, thank
everyone
you.
for attending the talk. this semester. This is the last semester, and yeah, give a final applause to Rohan. And
No, thank you, and all the best to everyone for the final exams. Hopefully, it's not very difficult with
yes, yes, yes. Okay, cool. So I'll see you our next semester or whatever in the future. Okay, take care. Bye.